And we know what's the difference between machine learning and econometrics, and we have some backgrounds in the statistics and mathematics, hopefully. And now we are learning machine learning, right? The reason is that I cannot jump into deep learning is that the basics of deep learning is machine learning. So we have to go over those simple models first and then move on. And just keep in mind that all of these things sometimes are answering the same questions. But think of it this way: deep learning is a subset of machine learning. Machine learning is a subset of AI, right? And we're going to talk about the details later on. Okay, so let's start by definition of machine learning. So what is machine learning? There are many different definitions. This is one of the best ones, in my opinion, and I took it from the textbook, Advances in Financial Machine Learning. This is a PhD level textbook, but the author is Marcos Dupredo, Marcos Lopez Dupredo. He's a finance professor at Columbia, but he works in salient industry, and he was the quant of the year last year. And his book is called Advances in Financial Machine Learning. If you ever want to continue machine learning in finance, so this is the best reference. So he summarized it like this: a machine learning algorithm learns complex patterns in a high dimensional space without being specifically directed. Okay. So there are some terms that we need to highlight here. So let's start with the last part, without being specifically directed. So I believe this has something to do with Abraham's question that says that, okay, how machines are learning without being specifically directed, right? First of all, we are programming them. So directed means that we are not constraining them with some functional forms. You will see lots of examples, but let me give you a little bit of background here. So without being specifically directed means that, unlike with other empirical tools, we do not impose a particular structure on the data. Instead, researchers let the data speak. So what does this mean? It means that, guys, remember, for example, in simple linear regression, we put a specific structure to the model. We say the model should be linear. Do you remember this one? See, this is imposing a specific structure to the model, to the data, right? Does everyone understand? So in machine learning, we say, okay, it learns without being specifically directed. So your first question should be something like this. Okay, so why regression analysis is machine learning? So this is difference. So what do you think is going on? Do you understand the question here? I'm telling that machine learning, the machine is going to learn without being specifically directed. However, in our first model that we learned in the class, multiple regression analysis, I'm imposing this restriction to the model. Yeah, David, go.
So would the comparison be, for econometrics, we set the linear model. In machine learning, we program to a certain point of the data, and it figures out essentially the functional form that it should be taking?
Yeah, David is saying that in econometrics, we specifically tell that the relationship is linear, but in machine learning, we don't do that, right? So my answer is no. So that's why I want you to understand this slide, okay? Again, this is very subtle point. I want you to realize that the definition of machine learning, it's not complex pattern and high dimensional and without being specifically directed. Sometimes it's simply or. Does that make sense? So, for example, in this here, as you can see in the next week, we're going over simple multiple regression model. So the functional form is exactly given, as simple as this linear model. But it's still, I call it machine learning. Why? Because maybe the models that we're handling are very high dimension. Or the data, we're talking about big data. So for some reason, I have access to the real-time, millisecond data. And I want to simply impose a very simple model like this, but the data is very, very granular, right? Or the dimension is, we're talking about thousands of variables, not only 5, not only 10. So does that make sense? So that's why I say that there's a difference between regression analysis in a statistical learning world and multiple regression in the machine learning world. So I want you to look at this definition, but at the same time, do not think of it as and, it's or. So sometimes, in simple regression analysis, we are specifically telling the model what to do. because it's linear model. And we say that, okay, use OLS and do the job and things like that. Okay. So that's one part. The other part is that it learns complex patterns. So the machine learning algorithm may find a pattern that cannot be easily represented with the finite set of equations. So this is the second part, that we are going to make that functional form more flexible. This is a part that statistical learning is going to completely diverge from machine learning, right? Because we're not saying that use this f of x like linear. So just, you will see when I talk about the neural nets or random forest in machine learning, you will see that the machines are very flexible. They can think of any kind of relationship between the variables, right? A quadratic, any kind of polynomial interactions and things like that. Then finally, this high dimensional space is, of course, is a big deal, right? Sometimes, many times actually in finance, we are dealing with many variables. And guys, when I say many variables, I don't mean 100, 200. I mean thousands, right? And then when it comes to deep learning, we're talking about millions of variables, millions of explanatory variables. There is no way that you can interpret that, right? And you don't care, you don't want to interpret that, because that's a job for machine learning. So I want to pause for a second here, make sure that everyone understands what's going on with the definition of machine learning and what's the difference between the two. Just stare at this slide and this slide and tell me if there is any questions, because this is important. If you don't understand it here, you're going to have a hard time. And if you wanted to test someone if he knows machine learning or not, just ask this simple question. What's the difference between regression analysis in econometrics and machine learning? Very few people can answer that. I hope that you can answer it now, okay? Question, Ryan?
Hey, Pedram.
Yep.
All right, so is it fair to say that in econometrics, we do we have the data, then we do hypothesis testing. In machine learning, does the machine do hypothesis testing, or does it directly go to the data and start identifying patterns?
Very good question. No, in machine learning, we do not care. We cannot care less about the interpretability. So what is hypothesis testing? At the end of the day, you have a belief, you want to test that with the data. In machine learning, that's not your goal. Your goal is you want to make predictions, right? So that's one of the main difference between the two.
So if I may ask a follow-up question, so if we don't care about interpretability and we care more about prediction, then how do we evaluate a machine learning's prediction if it's accurate or not?
So that's something that we're gonna learn together, right? So it depends on the model. If you're talking about a regression analysis, we can look at even adjusted R-square, or now that we are in machine learning world, we're gonna talk about mean squared error. We will look at a combination of bias versus variance. We talked about this in econometrics, but again, don't worry, we're going to talk about it in next class, next Monday a lot. But the goal is to compare statistics that compare to bias versus, it's a combination of bias versus, it's a trade-off between bias versus variance, right? So that's only one measure, Abraham. There are lots of other measures like AIC, Archaic Information Criteria, BIC, but the most famous one in the regression world is, let's say, that MSE, mean squared error. And in the classification world, we talk about accuracy, recall, precision. These are, again, there are lots of definitions that we're going to cover. But in regression analysis, you can think of an overlap between econometrics and machine learning, which is MSE, mean squared error. We could have calculated mean squared error in econometrics as well, right? So that's it.
Thanks.
Sure. All right, now let's move on. So here is the general difference between what is programming versus machine learning. So historically, we have been trained to code like this, right? So for example, we have an input, and specifically we give the computer the program, right? So for example, in the Python crash course, you saw me going over defining the definitions, right? The functions, defining the functions, right? So one of those functions was like add 10. I call it add 10. So the input was give me any number, and the program, I specifically told the computer, whatever you take, add 10 to it, and then generate the output. Does that make sense? So that's general programming, right? In the machine learning, the story is different. We give the computer inputs and outputs, and sometimes we don't even give the output. If I give both input and output, what is it? Supervised. If I only give the input, what is it? Unsupervised. Is everyone following? Okay. So we give them inputs and output to the computer, and then the computer is going to figure out that what was the pattern, what was the functional form between these variables that you gave it to me. You gave it to me, right? Think of it like this. I give you 10 tuple of numbers, right? 10 numbers. Let's say, so I give you 1 and 2, and the output is 3. I give you 4 and 5, the output is 9. I give you 10 and 11, the output is 21. So what is the function here? Summation, right? This is exactly like that. But I didn't tell you that the function was summation. You figured it out. So in real world, it's not that neat. Of course, data comes with a lot of noise, and we have to talk about those noises as well, right? But the idea is exactly the same. Give me input and output. A computer will figure it out on its own based on something. Again, Abraham, we are coding it, right? We're going to say that these are the cost functions, minimize that cost function, and based on minimizing that cost function, you will realize what was that functional form. In this example, simple example of ours, it was summation. Right? So this is the world of machine learning versus general programming. Is this clear, guys? Again, this class is very important. This is the building block for the entire course. So if there's any confusions, we have time, just let me know. Okay, now let's talk about different types of machine learning first, and then I'll move on and talk about AI versus deep learning versus machine learning. Okay, so the 3 different types of, well, again, guys, depending on what textbook you're looking at, some people do not think of reinforcement learning as a machine learning, but don't get stuck in these kind of definitions or where's the borderline. There's no clear-cut line, right? If you read the Tibshirani Hasty textbook, the main textbook for the class, they say that even there's a very, very fine line even between statistical learning and machine learning, right? So let alone these things, right? And those are the founding fathers of statistical learning. So don't think that, okay, so for example, my professor in this course says that the reinforcement learning is part of machine learning, but I read it online, it's not. Again, it's not clear cut, but as long as we understand the basic of all of them, I think we're in good shape. So let's focus on these 3, let's call them 3 types of machine learning, but I understand, I personally sometimes definitely see why people do not put reinforcement learning under the machine learning, but again, that's a separate topic. We will see some examples. Let's for now assume that these are 3 different types of machine learning. And we are going to cover the supervised and unsupervised in the class. So we are not going to cover the reinforcement learning, but you should know the difference, right? So if I want to give you a simple example of what's the difference between these 3, supervised versus unsupervised versus reinforcement learning, I think I'm going to give you a very naive one. And maybe it's laughable at first, but whenever you think of the difference between these things, if you think of this example, I think it will be very clear in your mind what's going on, right? I have a 13-month-old baby, and I'm seeing reinforcement learning and unsupervised learning and supervised learning every single day that I'm playing with it. It's fascinating how human brain is working, how this AI has been replicated from human brain. And the more I know about these materials and the more I watch my baby, it's fascinating how they're learning things, right? So let me give you an example. We have one of these touchless forehead thermometers at home. I think everybody has it these days. And then I'll set up 3 scenarios for you. So the first one is that I use that thermometer on my own forehead, look at the degree, and then either smile or cry, something like that. Then my wife does it. Then we give it to Dara. It's my son, right? So Dara understands that he has to put it on his forehead and then look at the number, right? If it is green, he's happy. If it is red, he's not happy. So what type of machine learning do you think it is? Everything is labeled here. Does that make sense? So it is supervised, okay? Now, let's explore the second scenario. So my wife doesn't do anything, I don't do anything, and we give this thermometer to my son Dara, right? And well, let's start. Well, you guess which one is that. And we let him play with that thermometer, okay? And we don't tell him what to do. Use it for your forehead, maybe stir your soup, whatever. We don't tell him anything, but we just monitor him. So he starts maybe putting that, not maybe, this is what he does every single time. He put it on his mouth and then start to play with that. And me and my wife, both of them, we give him a frown and said, no, 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 no. And then he correct himself. So what type of machine learning is that? That's reinforcement learning, right? Because what is the environment? So environment is we're sitting in front of him, and he can do some set of predefined actions, right? Whatever he does with this thermometer, right? But he still receive. There's no data here, label or unlabeled. We move on, and he will receive some feedback from the environment. What was the feedback? You say no, 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 yes, 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 something like that, right? So that was reinforcement learning. The third example is that we give him the thermometer, and whatever he does, we give him the poker face, whatever. So what is this? This is unsupervised. So why on earth should I do something like this? Again, in this silly, yeah, go ahead, Ryan.
So unsupervised learning would allow for the machine, or in this case, your baby, to maybe find different uses for whatever, the thermometer in this case, that you don't already know.
Exactly. Is everybody following? This is exactly what, again, this is a very naive example, but we are going to see, and that's why on earth we want to do unsupervised learning, regardless of the fact that the data is labeled or not, right? Sometimes the data is labeled, but we want to treat them as unsupervised. Sometimes the data is not labeled, you cannot do anything, you have to do unsupervised, right? But back to Jennifer's really good question, that do we ever go in after labeling the data? So that's a separate thing, right? But right now, is this clear what's the difference between these things, supervised, unsupervised, and reinforcement learning? So reinforcement learning and supervised, the agent is going to receive some feedback, either from the environment or from the data itself. But in unsupervised, nothing. Just always think about the poker face, okay? And what is the lesson learned for me? For example, me and my wife, we realized that you can stir your soup with just a thermometer, right? Forehead thermometer. So again, is it useful? So the answer, sometimes in finance, we can backtest and realize that if it was useful or not, but in many applications out there, you never know. You're just curious to explore the new patterns. In a way that it's not normal for us, right? So let's say untraditional, okay? Okay, so I hope that this example helped you out with what's the difference between supervised versus unsupervised versus reinforcement learning. Now let's quickly go over the actual definitions. I guess everybody knows these things, so I'm gonna speed up here. And then I will focus on the applications in econ and finance here, but we're going to work with 12 data sets for this course. And guys, it used to be 2 in last semester. Now it's 12, thanks to your previous generation. You can do worse for next generation, but it is good actually. You're gonna work with lots of more data sets and lots of more applications, right? So these 12 data sets, I think I cooked it last weekend, I think last month, let's say. I think 50% of it is going to be finance, and then 20% is going to be econ, 20% marketing, and 10% just general, so something like that, right? So we're gonna deal with many different applications of machine learning in this course. But the examples that I have here on the slides for the next couple of slides, it's purely finance, okay? Okay, so what is supervised learning? I think that we all know that the computers are gonna learn to model relationship based on labeled training data. Oh, I forgot to talk about training data validation set and test set. This is also straightforward. We're gonna talk about these things a lot more, but guys, remember, we have a data set. Let's say this data set has 100 observations. We're gonna take 70% of that data set to train the model. What does that training the model mean? Do you remember I gave you an example, 1, 2, 3, 4, 5, 9. So this is this is the part of the data that I gave it to you to train you. Then you're going to save 10 to 15% of the data to validate the model. What does validation mean? So my model has some parameters. I'm going to go ahead and use those new data that the model has not seen before to validate the parameters. And then finally, I'm going to test the model on some part of the data, let's say the remaining 20%, something that the model has never seen. Because if I this is machine learning, the models are super flexible. If I test the model on some data that the model has already seen, not surprisingly, you're going to get perfect answers because the model was trained to do so, right? So you have to test it on something that the model has never seen before. Why? Because going forward, I don't know what's the stock price of Apple. I know it for yesterday, so it's not fair to test it, right? So that's the difference between train, validation, and test, and we're going to talk about these things in the class. All right, so supervised learning, there are two general types of, classes of models. We have regression models and classification. So regression, I think, yeah, we had a comments here as well. So I got a comment, so when do we do regression, when do we do classification? So what's the difference between continuous random variable and a discrete random variable or categorical random variable, right? So what is continuous random variable? Like many variables that we see out there, wage, price, things like that, right? So these are all examples of continuous random variable. If you want to predict a continuous random variable, we do regression analysis. So this is regression analysis, right? We want to predict wage, so this is a continuous random variable, so we call it regression analysis. If the variable of interest, in machine learning, we call it target variable. If the target variable is categorical variable, or binary variable, or different classes, we call it classification, right? So the engines behind these two types of model, regression versus classifications, are going to be different for any single model that we use in the class. So that's a separate topic, right? But remember, what's the big difference between the two? So if your target variable is different classes, we call it classification. If your target variable is continuous random variable, we call it regression analysis. Is this clear? Okay. So let's look at some example. In regression, so for example, I'm going to predict your wage. Yeah, that's regression. I'm going to predict the stock market return. Regression. Why? Because the market returns is a continuous random variable. I want to predict revenue growth. This is regression, right? And what are some examples of classification? Imagine we want to generate a buy, sell, hold signal. So what is the target variable? Buy, it's basically the signal, right? Signal is going to be my target variable. What are the different classes? Buy, sell, hold. So I have 3 classes. At the end of the day, I want to run some model, and that model tell me that at the end of the day, is it buy, is it sell, is it hold, right? I want to run a model to see if you fail or pass the course based on previous information. What's the target variable? Fail or pass. Okay. As long as the target variable is discrete, is categorical, we call it classification. Otherwise, we call it regression. Is this clear, guys? All right. Another example, the likelihood of a successful M&A or IPO. So this is merger and acquisition. IPO stands for initial public offering. So you want to, and I have to add SPAC after 2020, right? So we have lots of SPACs. And so basically, we want to see if an IPO is successful or not. So we have a history of IPOs. So we do some maybe a regression analysis or things like that. And at the end of the day, I want to see what's the probability of success for this new SPAC, for this new NMA going forward, okay? Then let's say enhancing detection of fraud in financial statements. So what is the target variable? Fraud or not, no fraud, right? 0, 1. Classification on winning and losing funds or ETFs. So this is exchange traded fund like mutual funds. Again, guys, there are some explanation in this CFA reading, but if you don't have finance background, don't sweat over it. It's no big deal, okay? It's really, we're going to talk about the models in a more general way, but whenever it comes to the specific finance examples, data sets in the class, I'll try to be more clear. Okay, so that was a supervised learning. Remember, we have both input and output, and then everything is labeled. Now, think of me and my wife are showing what to do to our son first, and then expecting to do something. So this is the supervised. The unsupervised. So what is the unsupervised learning? Computers are trained on unlabeled data, so we know that there is no output. Sometimes there is no output. In the data, there is really no output there. Sometimes there is, but you don't give it to the model. Is this clear? Okay. Most of the time, there is no output. So the data is not labeled. So we're going to look at some examples. The data is not labeled, and so we cannot do anything about it. So we have to just use some unsupervised machine learning models to just realize what potential patterns are in this data, what potential different classes are in this data. Does that make sense? Okay. And so there are two models, the two groups of models here as well. Like, remember, in supervised we have regression classification. In unsupervised we have clustering versus dimensionality reduction. Okay, so let's talk about either of them. So what is clustering? So clustering is exactly the same as classification, but because there is no label there, we just call them clustering. We don't know what are the names of the class, so we don't call it classification. We call it clustering because we want to sort the data based on different clusters. Okay, so that's why we call it clustering. What are some examples? For example, I don't know, I have 500 companies, right? Let's talk about S&P 500. So what is S&P 500? The 500 companies that, Fortune 500 companies in the stock market, and they have to meet some criteria like profitability for some certain quarters. After meeting that requirements, they will be part of the S&P 500, right? So usually, how do we classify those 500 companies? Based on industry, based on sector, things like that, right? We have 11 sectors in finance, in stock market. Said, okay, this is consumer discretionary, technology, consumption, things like that, right? So we have 11 sectors. So usually we do that kind of clustering. We have some prior belief. Is everybody following? But in unsupervised learning, I'm going to say that I don't care what's the sector of the Apple. I don't care what's the sector of Tesla. I don't care what's the, even though I know it. Do you understand the difference? Even know what's the sector of the Tesla, Apple, Microsoft, but I assume that I don't know it. I want to see what data suggests, right? And I'm going to use some non-standard characteristic like financial statements or corporate characteristic or co-movement of the stocks, right? So I'm going to say that. So this is an example that actually we're going to cover in the class. This is in the CFA reading, and I'm going to cover it in the class. So imagine I have Facebook, GM, Apple. This is Ford, sorry. Ford, GM, Apple, Facebook, Google, and Goldman Sachs, JP Morgan, and UBS, right? So usually we think that, okay, Ford and GM must be in the same group, and then maybe Apple, Facebook, Google in the same group, and Goldman Sachs, JP Morgan in banking sector, right? So this is what we believe. However, we're going to use co-movement of the stocks. Instead of looking at the sectors, I'm going to see, I will look at the return of the stocks and see how they behaved. Maybe the behavior of Ford is very much like Facebook. I didn't think about it before I do this analysis. Is that clear? So that's why we do unsupervised learning. And actually, we're going to run this exercise in the class. Is everybody following? Okay. And so another example, client profiling and asset allocation. Again, historically, if I can give you information, for example, about, I have hundreds of clients and I want to do some asset allocations for them, right? I look at their age, I look at their risk aversion, things like that. And at the end of the day, I say, okay, if you have some rule of thumbs, right? We say, okay, 70 minus your age, 100 minus your age goes to the equity, the rest goes to bond, some rule of thumbs like this, right? But I'm going to get away from all those things, from all those predefined beliefs, right? I want to see what the data suggests. Maybe the data will put a 70-year-old with a 20-year-old based on some new characteristics, right? This is what Amazon is doing. If you look at Amazon, we're going to look at an example. I think it's going to be bank customer segmentation, which is a really interesting data set. We're going to take a look at that one too. So for each of these examples, I have a data set for this course. So that's why I'm super excited about this semester. Third one, portfolio diversification and stock selection based on co-movements of similarity. So again, we're going to talk about these ones. So, but I think you get the idea. What's the difference? So the second type of the unsupervised learning is dimensionality reduction. So what is this one? So in general, dimensionality reduction, we're talking about the dimension of the feature space. So terminology, guys. In econometrics, what is explanatory variables? The variables on the right-hand side, right? These are we call them explanatory variables. In machine learning, we call them feature space. Just different name, okay? Feature space. So feature space, and then in econometrics, we call this, let's say, independent variables, dependent variable, or explanatory variables, explained variable, things like that. In machine learning, just two names. It was just one name, right? Feature space, target variable. Just remember these two terms. Feature space, anything on the right-hand side. Target variable, your target variable, the left-hand side. Okay, so when I talk about dimensionality reduction, I'm talking about the feature space. So we're talking about the feature space with hundreds of variables. In some examples, you'll see lots of the data sets that we're going to use in this course. The number of feature space is less than 50, 40, so that's no big deal. This dimensionality reduction usually is the case for example, two applications. You're dealing with thousands of features. In medicine, you literally have those thousands of features. In finance, we also have those as well. And you want to reduce it, let's say, to 10. And you want to reduce, instead of thousands of explanatory variables or feature space on the right-hand side, you want to work with 5 of them, 6 of them, 10 of them that explain the majority of the total variation of the target variable. Did everyone follow this last statement? And again, we're going to talk about the details of PCA. We call it principal component analysis later on, but that's the gist of it, right? And sometimes you want to visualize things, even though we have 10, imagine I have 1, 2, 3, 4, let's say 10 explanatory variable or feature space on the right-hand side, right? Can I visualize it? No. Our human eyes cannot handle more than 3-dimensional space, or maybe some people 4-dimensional space, but not beyond that, right? So if I want to visualize this thing, I'm going to use principal component analysis to reduce the feature space to 2, only 2. What's the name of them? We don't know. I call them PC1, principal component 1, PC2. PC1 and PC2 is a linear combination of all those 10 features. Again, I don't care what's the name. The cool thing is that I can now visualize. I can have horizontal axis PC1, vertical axis PC2, and see where the data lays out. Does that make sense? So that's the use cases of principal component analysis. What's the finance? Actually, I haven't worked on this data set, but I'm excited about it, and I have time until the end of the semester to come up with. I'm writing a paper on this one, actually. Hopefully, by the time that I'm presenting, which is the last couple of weeks of the class, the data is ready, the model is ready. But in finance, have you ever heard the term of zoo of factors? In factor modeling? What is factor modeling, asset pricing, finance? Okay, so let's say we have different stocks, right? And we can, have you ever heard the term CAPM, capital asset pricing model? So we know what is CAPM. For example, Apple stock, we look at the sensitivity of Apple stock and Microsoft stock or any individual stock versus the market. If market goes up and Apple goes up one by one, the beta, the sensitivity is 1. If market goes up, Tesla goes 1.5, so the beta is 1.5, right? Up and down, right? So this is what we call CAPM, capital asset pricing model, right? So there's only one factor. That one factor is market return. Look at the market return and just quantify the sensitivity of your individual stock toward that market return. So this is one factor. In finance, there are hundreds, if not thousands of those factors, right? So I happened to introduce one of them in my PhD, thesis for PhD, right? Which was financial obligation ratio. For example, if you're more stressed in terms financially, you will become more risk averse and things like that. So there are literally thousands of researchers out there coming up with different factors, and there is a zoo of factor out there, right? I think in the literature, there are more than 200 good ones, right? So I'm going to use this PCA analysis, dimensionality reduction, to reduce those factors into only 2 or 3. We're going to see maybe 2 principal components, which is a linear combination of all those factors, that's going to summarize the majority of the variation of my stock return. Does that make sense? I know it's going to be a little blurry right now, but by the time that we get to PCA, you are an expert in machine learning, so you can handle this conversation a lot easier. Okay, you good? All right. So far, whatever we covered is going to be included in the course. From now on, everything that I discuss is not in the course. It's just for your own general knowledge to understand what is the big picture. Okay, so from this slide onward, it's not in. This is not what we cover in the course. So the first one is reinforcement learning. So I think all of us know what is reinforcement learning by that example, but it involves computers learn from interacting with itself, right, with its environments. So we have to, however, we have to define the environment. So I have to say, okay, this is the environment that it can explore and exploit in that to the agent. What is the agent? Agent is your computer or whatever. And then we have to also define the actions, right? So for example, remember that thermometer example? No, I have to define the actions for Dara. So you cannot do this set of defined actions, well-defined actions, right? Not anything beyond that. So maybe humans can go do anything beyond that, but computers, you program them. You tell them what are the actions, okay? So you give them the actions, you give them the environments, and finally you give them the reward, the feedback, right? That smile or frown that I gave to my son, right? So you give them the feedback. And then agent, by going over thousands of simulations, is going to figure out what is the output, what is it, we call it policy path. What's the policy path? So what is policy path? If I was in this, I don't know, this step, do that. If you're in this cell, do that. If you're in that cell, do that, right? For every single space in the environment, the output is going to be one well-defined action. Is everybody following? Okay, so this is reinforcement learning. An example in finance, so here's an example. Imagine a virtual trader, an agent. We call it agent, right? Who follows certain trading rules. So these are the actions. We have to say these are the things that you can do, buy, sell, short sell, things like that, right? In a space, in a specific market, so this is the environment. So the environment is the stock market. To maximize its profits, so what is the reward? It's going to be profit. And you're going to let the agents do its job. So of course, the first couple of runs of the simulation is going to be very, very poorly because maybe the portfolio is losing money, but you say that you're doing it wrong, right? So then it's going to optimize itself. Go back, do it again, and eventually you will come up with an agent that, if you put it in the stock market, based on, again, this is the black box part of it because reinforcement learning involves lots of neural networks. Knows that based on the state that I'm staying right now, what to do, maybe buy. So buy is doing good, and then maybe another buy, good, another buy, it's losing money, right? At the end of the day, there's a trajectory for every single of these paths, but it will be optimized at the end of the day. This is very exciting and works for lots of applications like self-driving vehicles. You know, Tesla is doing a perfect job. NIO, the Chinese company, is doing a perfect job here, right? So and you're going to output human easily. You know, I emphasize, you know, I cannot see we in US are driving in the next 5 years. No way. My kid is not going to have a driver's license. I have no doubt, zero doubt, because by the time he's 20, we're not driving at all. Again, maybe the transition is going to be slower, but if he chooses, he can decide not to get a driver's license, right? Because in those kind of applications, it's accurate, but in finance, it's very, very in its baby step now. It's very, very novice, because in finance, the portfolio, or at least the ones that people are publishing, it's not working, because finance is a lot more complex than self-driving cars, a lot more. It involves humans, and humans are very, very scarce and different beast in the world, right? So this is reinforcement learning, and the reason that I will not focus in the class, first of all, it's the entire course itself, and it's not promising in finance yet. Okay, so how are we doing in terms of time? 10 minutes, so I should be able to easily finish the rest of it, because we talk about AI, machine learning, deep learning. So AI is not a new thing. It was there since 1950s, but because of the limitation of computing power and storage power, they gave up on the idea because it was costly. 1980s, we call it AI winter, because the cost of the researcher was a lot more than the results. So they stopped the entire AI thing back then. But now, as the computing power improved and we have lots of storage, cloud storage things going on, then the machine learning evolved, and then the deep learning evolved. So for deep learning, we need a lot more information than machine learning, and for machine learning, We need a lot more information than AI. But think of it this way. Deep learning is a subset of ML. ML is a subset of AI. OK, so what is deep learning? Deep learning is very much like the machine learning itself. So it can have supervised, unsupervised, exactly the same, and reinforcement learning. And usually in reinforcement learning, we use neural networks. The idea is that, so this is what we call neural network. And this is, these algorithms are inspired by human brain, right? So these, the yellow ones are input layers. Input layers are something as simple as this: education, age, experience, right? This is the input layer. Output layer, this again, if it is usually it's classification, it's either buy, sell, hold, right? So this is output layer. What is in between? In between is, we call it hidden networks. And those hidden networks can be any combination of these input layers, right? So imagine I think I want to combine education and age together and put it here. Does that make sense? It's not only that, it's a combination of anything, right? Education, age, experience, all of the different paths there. And it's not even one layer. So this is, we call it neural network when there's one hidden layer. We call it deep neural network when it's multiple hidden layers, right? So think of it. I have age, education, experience. Maybe here I can keep track. Maybe look at this one. It has some components of age, education, and experience, 3 of them. Maybe there is interaction, quadratic, whatever. But when I go one step further, this is another hidden layer. I'm lost, right? So there is no way you can keep track of what's going on in a neural network. So deep learning is absolutely black box as of today. As of today, it's absolutely black box. So you cannot interpret anything, right? But it's insanely powerful. So we're going to talk about, when I talk about the cost function and things like that, I'll tell you there's a theorem out there that you can literally approximate any kind of function using deep learning, using neural networks. So that's how the deep learning is doing its job, but the basics are exactly the same as machine learning. So we have input, output, supervised, unsupervised, but the mechanism is different. It's a lot more flexible than machine learning. Does everyone understand why it's more flexible? But because look at that. It's considering any kind of combination, any kind of pattern that there exists between the variables, right? And what is this one? What do you think? What is this one? Any guess? It's a typo. Okay. Yeah, this is a typo. It shouldn't be here. Okay, because we have hidden layers. All right, examples, image recognition. You can think of, there's huge application of image recognition in medicine, detecting tumors in different parts of the body by going over millions of records of images. And for example, by image recognition, we can do shipping activity and manufacturing facilities or yields on agricultural crops. I have a friend working for a winery, and they look at the satellite pictures. They see if it is worth to go for harvesting this season at this time or not. These are insanely useful things, right? All right, so this is deep learning, and then NLP. This is next one is natural language processing. So now this is more of an AI. So we know what is machine learning, what is deep learning. Now it's more of an AI, it's the natural language processing. Everybody knows what is NLP. What is NLP? When you talk to Siri, when you talk to Alexa, when you talk to Google, this is NLP. Just real time, try to translate your word into computer language and then make sense and sentiment out of it, right? So it's an intersection of computer science, AI, and linguistic, and focus on interpreting human language. So what are the applications? Automated tasks using NLP include translation, speech recognition, text mining, sentiment analysis, and topic analysis. Look at some examples. So for example, look at that. So I don't know, 10 years ago, it was even impossible to think about going over all these records of the conference calls or, I don't know, the different company filings in the SEC, their earning calls, the statements, and things like that. But now, using NLP, we can read millions of pages of annual reports, thousands of hours of earning calls, literally listening to the voice, to the earning calls, right? And in transcripts, news articles, and things like that. At the end of the day, we want to get a sentiment out of that, right? So you want to listen to an earning call and then get a sentiment. Is it a buy or sell? There are companies out there that their job is to sell this information, right? So you can say, okay, listen to this to this earning call real time, and then give me a signal, buy, sell. Another example, so for example, I think we saw it a lot during COVID, right? Whenever Powell was making a speech, I think algo traders were trading insanely based on the sentiment of that speech, right? And chatbots, so I think every single of us have worked with chatbots. When you open your online banking, it's going to recommend something. So these are, again, we are living with the applications of NLP today. And then the last one is cognitive computing. So this is, again, this is a part of AI, and it only focuses on mimicking human behavior. It doesn't involve this decision making, just mimicking. So for example, what are the examples? Algo trading. So algo trading, do not confuse it with machine learning. So algo trading is the computerized buying and selling of financial instruments, right? In accordance to pre-specified rules and guidelines. So basically it says that if these conditions met, buy. If these conditions met, sell. It's not making any decisions, right? So algo trading, so this is not machine learning. So in the machine learning, we do make decisions. So this is part of we call it cognitive computing. And it's really hard to categorize it. Is it AI? Is it machine learning? But again, at least this is a classification that we have in the CFA textbook. And I think CFA textbook comes from a textbook itself. The author of this chapter is Matthew Dixon and Christopher Lanotte. Matthew Dixon, he has a book in, I think it's Machine Learning Application in Finance, From Theory to Application, something like that. This is a really, really famous book. And he's a very famous person. So the authors of the CFA chapters are not some random PhD students, PhD graduates like myself. These are people that have a very good history tracking record. And so another example of cognitive computing is high frequency trading. Just feel free to read through this paragraph. Basically, the high frequency trading is that it's not making decision. It's just looking at if some criteria is met, then you do something like that. We call it high frequency because the trades are based on milliseconds and even nanoseconds, right? They're usually look for misprices in the market. And believe it or not, the regulations on the high frequency trading is insane. The SEC is regulating the companies based on their distance from Wall Street, from the exchange. And when I say distance, the feet matters, because if your company is 100 feet closer to the exchange, you get information maybe some nanoseconds earlier, you can trade on it. So we're talking about this kind of efficiency in the US market. This is very beautiful, okay? The beauty of it is that, I think in my mind, the lesson learned is that don't waste your time by day trading. Okay, again, sometimes it works, sometimes it doesn't, but don't waste your time. It's a waste of time. You may talk to some of my colleagues, they have completely different opinion, but I have worked at BlackRock, I've seen people, I know what they're doing. Don't waste your time. You can be one of them, so that's a different story. But don't waste your time that you can beat the market. No way. Okay, so let me conclude our class with this slide, and then we're going to review these things throughout the semester a lot. So these are the models that we're going to cover: supervised, unsupervised. For the regression, we do linear and polynomial, KNN, SVR. Again, this is just a list, a laundry list of models that we cover. So there's no point of me going over them now because we don't know what are they. But classification, these are the models that we cover. Dimensionality reduction, there are multiple models. I only cover the PCA. And clustering, again, there are multiple models. I cover the most important ones: k-mean clustering and hierarchical. And this is a very good stylized decision flowchart for choosing machine learning algorithm. So this is something that I really want you to, again, at the end of the day, you have read this 70 pages and it talks about it. So maybe the next class, I'm going to start from here, basically how you should approach, what models you should look into before jumping behind your computer and try to coding things, right? You have to look at your data set, look at the characteristic of the data set, and then have some idea that which model is going to work better. Okay? And having said that, remember, the machine learning algorithm will always find a pattern. Will always, even if there is none. If you torture the data long enough, it will confess. So actually, we're going to have a lot of fun in one of our classes. I'm going to generate a random data. I'm God. I know what is the underlying, what's the real relationship between variables. So I sit as a God, but I generate some noise. And then I let the computer, let the machine to make the model as flexible as possible. The machine is going to come up with a pattern that I, as a God, know that that pattern is wrong. Does that make sense? So that's it. Is there any questions from the lecture, guys at home? Okay, I believe I covered everything I wanted. So next class, we will do EDA, explanatory data analysis. And I'm going to do an EDA. What is EDA? We're going to talk about it, right? So I'll work on a very simple data set in the class. And then I will walk you through different parts of that EDA analysis and see basically how we should stare at the data before thinking about even the models, right? And then your homework is going to be due on Monday, but I'll give you a template for homework.